Our final test for the convergence of a series is probably the easiest test because it's actually just an adaptation of our first test for convergence about the terms going to zero or not. And that test we're going to consider is called the alternating series test. Up till now, we've been considering the sum of positive numbers. All we've been adding up is positive numbers. Well, in the alternating series test, we're going to consider series that alternate sign. Positive, negative, positive, negative, positive, negative. So, for example, we have negative 1/3 to the n. That's 1 minus a third plus a ninth minus a 27th plus an 81st minus ... We also can consider what the alternating harmonic series, which is the sum from n equals 1 to infinity of negative 1 to the n plus 1, 1 over n. So it's the harmonic series, except now it's alternating. So when we're looking for alternating, you want to be on the lookout for negative 1 to the n, negative 1 to the n plus 1. We can also write this as the cosine of pi n. We discussed that that's also the same thing as negative 1 to the n. So looking out for these things is the tip-off that you have an alternating series. Also, if you write the first couple terms and they alternate back and forth, that's another tip-off. Here, of course, the negative 1 to the n is built into our term. Here, it's kind of out here by itself. So we have an alternating series. And the rule for these guys is incredibly simple. Is the series alternating? Do the terms go to zero? Sorry about that. If so, the series converges. That's it. If it's alternating and the terms go to zero, that's it. We're done. The series converges. Talk about easy peasy. Well, for the first one, of course, we know what the sum of this guy is going to be because we know our geometric series. That's going to be 1 over 1 minus negative 1/3. Sorry, negative 1/3. Or 1 over 4/3, which is, of course, just 3/4. However, we don't have a real simple solution for what this is going to equal. However, I can offer a graphical kind of convincing argument that this might, in fact, converge. So I drew the number line from 0 to 1. My first term, I'm going to add 1. Now I'm going to subtract a half. Now I'm going to add a third. Then I'm going to subtract a fourth. Add a fifth. Subtract a sixth. Add a seventh. Subtract an eighth. And I think you get the idea here that basically we're just spiraling in, spiraling in, spiraling in, and eventually we're going to land right there. We're going to converge to this point right here. And we'll discuss why later in this chapter. But here's a crazy thing for you. That number right there is the element of 2. So we'll get to why that's true later in this chapter. But the idea of the alternating series is that you add one piece and then you subtract the smaller piece. Then you add a slightly smaller piece, subtract the smaller piece. Well, if you keep adding smaller and smaller pieces, eventually it has to hover and then land at one particular point, and that is going to be what it converges to. So we can figure out it converges somewhere, and it's going to converge right there. We can use this spiraling in that occurs with alternating series to estimate the sum of our alternating series. So the idea is that we're going to try to estimate what the full sum is. And what the alternating series will tell us is that if we take the full sum, that's the sum from n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n, minus the series where we only take the first n terms, where n could be the first 3 terms, the first 10 terms, the first 100 terms, however many you want it to be, that the difference between these two guys will always be less than the next term in the series. So in this case, it's 1 over n plus 1. And pictorially, this makes sense. For example, let's let n equal 4. So we'll start here. We'll go 1, 2, 3, 4. That gets us to this point right here. And what we have claimed here is that the actual answer, which I have marked here in blue, is within 1/5 of our estimate. Our estimate right here is within 1/5 because our jump of 1/5 will go that far, and our estimate is within 1/5. So we could say, by looking at this guy, we can write this out as a statement of the alternating harmonic series minus, now if we just take the first 4 terms, 7/12, we're claiming that that has to be less than 1/5. The difference between the entire answer, which is marked here in blue, and my estimate using just the first 4 terms, which is this dot in white, are within 1/5 of one another. We can generalize this idea to say that if we take the infinite sum of an alternating series and then we compare it to the sum after only a certain number of finite terms, so this is all of the terms, this is just the first n terms, the difference between these two guys will always be less than the next term in your series. Let's try this with a series that we actually know the sum of to confirm the validity of this statement. So I want to consider the alternating geometric series -2/5 to the n power, which is of course 1 minus 2/5 plus 4/25 minus 8 over 125 plus 16 over 625, ... I'm going to consider just these first 3 terms as an estimate. So I'm going to take the entire sum, I'm going to subtract off those first 3 terms, and hopefully my answer will be less than the next term, which is 8 over 125. Of course, notice that I have to use the positive version because an absolute value is not going to be negative. But the way we defined it, we always said a sub n, and we left off the alternating part. So that does jive with what we said before. All right, well, of course, the series from 0 to infinity of -2/5 to the n is 1 over 1 minus -2/5. And if we add these 3 numbers together, we get 19 over 25. Well, this fraction simplifies to 5/7. That fraction is 19/25. If you get a common denominator of 175, you'll find out that this is -8 over 175. And obviously, the absolute value of this guy is 8 over 175. And 8 over 175 is definitely less than 8 over 125. So therefore, we know that our answer is within 8 over 125. If that's not accurate enough for you, if you want the answer to be within 16 6/25, go one more step. If you want the answer to be within 32 3,125, which is about 100th, that's about 100th. If you want it to be within 0.01, go out this far for 1, 2, 3, 4, 5 terms, and the resulting answer estimate you get from these 5 terms will be within 32 3,125 of the actual answer, which in this one case we know is 5/7, but for other cases we don't know what the sum is, and this can be really, really powerful for helping us estimate an alternating series. 3 quick examples for the alternating series task. Remember, all we have to check is it alternating and are the terms going to 0. That's it. All right, so let's look at this guy right here. Well, it definitely looks like it's alternating. So the real question is, do these terms go to 0? Yes, they do, because the ln of n plus 4 goes off to infinity. Therefore, we know that this guy is going to converge. Similarly, you can look here, -1 to the n, sine of pi over n squared. It is definitely alternating. And we also can tell that as n goes to infinity, this is going to be the sine of 0, which is 0. This guy is going to converge. Finally, we have -1 to the n plus 1. times the arctan of n. This is going to diverge. And that can be seen pretty easily because while it is alternating, these terms do not go to 0. They go to pi over 2. We know that as x goes to infinity, the arctan of x goes to pi over 2. Therefore, the limit of the arctans of n is also pi over 2, which is not 0. So this guy diverges. One final idea to conclude our discussion of convergence or divergence of series is to discuss the idea of absolute convergence. So we started off by saying our terms had to be positive, and then we let them alternate. Now we're throwing all that away and we're going straight to, you can give me whatever kind of terms you want. They can be positive, they can be negative, they can alternate, whatever you want, I can handle it, throw it at me. Absolute convergence is a series is said to be absolutely convergent if the series of the absolute values converges. So if you have a series where if you throw absolute value signs on it, it converges, that is considered absolutely convergent. It's convergent with absolute values, absolutely convergent. Couple quick notes. In our cases so far where an was bigger than 0, well then the series of ANs is the same thing as the series of the absolute values of AN. So far, everything we've talked about being convergent is actually absolutely convergent. So if you're positive, then you are the same thing as your absolute value. So convergence and absolute convergence are the same thing. Regardless of that, no matter what, absolute convergence automatically always implies convergence. If you can add up the absolute values and get a finite number, then you can certainly add the terms individually and get a finite number. And finally, if a series converges but does not converge absolutely, meaning if the series of ANs converges but the series of the absolute values of ANs diverges, then we say that the original series is conditionally convergent. The condition being that you let things not always be positive and going in the same direction. So conditionally convergent is on the condition that you let some of the terms be positive and some of the terms be negative. So I'd now like to return to our previous 3 examples. So we're looking at our first series and we realized that this guy was convergent. Now the question is it absolutely convergent? Is it absolutely convergent? Well, let's consider the series 1 over the ln of n plus 4. Well, that is, of course, the absolute value of this guy right here. Notice the absolute value just throws the alternating part away. Got this guy, and we know by our discussion of comparison tests that this is bigger than the series 1 over n plus 4. The ln of n plus 4 is less than n plus 4. Therefore, 1 over the ln of n plus 4 must be bigger than 1 over n plus 4. Therefore, this guy diverges. So we're going to say that this guy is conditionally convergent. And we use the abbreviation CC, conditionally convergent. Next, we'll consider our example of -1 to the n times the sine of n and pi over n squared. So, of course, I want to ask, is that absolutely convergent? That's asking about the sine of pi over n squared. So we have to ask ourselves, does this converge or does this diverge? And you have a couple different techniques to use. The technique I'm going to employ is the limit comparison test. I'm going to think about the limit as n goes to infinity of the sine of pi over n squared divided by 1 over n squared. And the reason I chose n squared is because that's what's sticking out as far as a power to me. I see that n squared right there. And I will leave it up to you to check that this limit in fact equals pi. So this limit equals pi. Therefore, because it equals pi, which is non-zero and finite, we know that these series either both converge or they both diverge. And of course, I know that 1 over n squared converges. Therefore, we're going to come back over here. We're going to say that this guy is absolutely convergent. Use the letters AC. Conditionally convergent, absolutely convergent. This guy was divergent before, it's divergent now. So the divergent part doesn't change. But notice we have two different classes of convergence. So instead of asking does this series converge or diverge, the new question is does it converge absolutely, does it converge conditionally, or does it diverge? So we're going to kind of open up our answer a little bit. That concludes our discussion of tests for the convergence of infinite series. So we do have several tests, which I will remind you of now.
Step 1 is always to check if the terms go to 0. Because if the terms of the sequence do not go to 0, the series is definitely going to diverge. We next then ask, is it a p-series or a geometric series? If so, we apply the appropriate rules. Finally, we check if it's an alternating series and apply that rule. Of course, the alternating series test can only give us conditional convergence. In order to find absolute convergence, we will always need another test. Those tests include the comparison and limit comparison test, in which we compare the given series to either a geometric or a p-series that looks similar to our series. Of course, we can always use the integral test, but as I've mentioned, that's my least favorite, and therefore the one I use only as a last resort. And finally, my two favorites, the ratio and the root test.
All right, so I look forward to seeing you in class. Have a great day.